In this first video for the logic unit, we are going to be talking about one of the types of reasonings that we're going to see throughout the unit, and it's called inductive reasoning. And inductive reasoning is when we are making a conclusion based on observations and patterns. In other words, this is when we predict the next pattern, or we predict the next term in the pattern, which is we're going to be looking at what the pattern is, and it could be with numbers, could be with situations, could be with letters, time, it could be any of those things that we're just going to predict what comes next in that pattern. So a conjecture is a concluding statement that is reached using inductive reasoning, and the other form of reasoning, which is deductive reasoning, that we're going to learn about later. So now, when we look at the first example on here, we need to find the next 5 terms of the sequence and then write a conjecture about it, of what we are noticing with the pattern. So basically describe what the pattern is. So if we go from 38 to 31, that actually decreases by 7. Let's see if we continue that. 31 minus 24 does decrease by 7. 24 going down to 17 does decrease by 7, so we need to continue that pattern. So to generate the next term, we are going to be taking the previous number and subtracting 7 each time. So when we continue that in our pattern up above for the actual next term, 17 minus 10, or minus 7, sorry, gives us a 10. 10 minus 7 gives us a 3. 3 minus 7 gives me negative 4. Negative 4 minus 7 gives me 11. Negative 11. And negative 11 minus 7 more gives me more negative, so negative 18. All right, so for example number 2, I want you, well, I'll help you on this one, then I'll let you do the next one. So for our number 2, if we look at what the pattern is, it goes from 2 to 5, so that's 3 more. Then, let me write that, so plus 3. Then from 5 to 11, they added 6. From 11 to 23, we end up adding 12 to it. So one thing you can notice is that it's doubling each time. Or a different way of thinking of it, look at how the 3, oops, sorry about that. Look at how the 3 is 1 higher than the 2. The 6 is 1 higher than the 6, or than the 5. The 12 is 1 higher than the 11. So if this is 23, the next one should be a plus 24, which would give us 47. 1 bigger than 47 is plus 48, so if I add 48 to it, that gives me 95. Then if I add 96, so 1 more than that, would give me 191. If we add 192, we would get 383. And if we add 384 to that, then we get 767. So one way of describing that is we're taking the previous term, and we are doubling it. So 2 times 2 is 4, and then I add 1 more to it. That's one way of doing it. Or we can say that we're taking the previous term and we're having the previous term plus 1 added onto it. All right, so now for number 3, I'm going to do this one, and then you're going to do number 4 by yourself on the next one. So if we notice, it goes from 1 to 4 to 9 to 16. Think of it went up by 3, then by 5, then by 7, but that doesn't, it's increasing by 2 more than the previous term. Another way we can think of that is to get 1, we can take 1 squared. To get 4, we can take 2 squared. To get 9, we can take 3 squared. And to get 16, we can get 4 squared. So let's think of it that way. So 1 squared gives me the 1, 2 squared gives me the 4, 3 squared gives me 9, and 4 squared gives me 16. So the next one should be 5 squared, so at 25. And then 6 squared would be 36. 7 squared would be a 49. 8 squared would give us a 64. And then 9 squared would give us 81. So each element, so element are the numbers, so each element is the square of the term number. And if you count them with me, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So notice that the 9, 8, 7, 6, 5, 4, 3, 2, 1 all goes with those different numbers as well. So those are the term numbers. So if we take the square of the term number, that's one way of determining what it is, or we can just say to generate the next term, you need to square the nth term. With problem number 4, we're going to work out the pattern now using letters. So you have to figure out how many spaces are between each of the letters, or how many letters are between them. So between A and D, there are 3 letters. Between D and G, there are also 3 letters. And between G and J, there are also 3 letters. So if we continue that same pattern, you can see up above that we had A, D, G, J. So if we continue the same pattern, we would end up with M, P, S, V, and Y. So our explanation is to generate the next term, you want to take the previous letter and add 3 letters onto it. All right, so for number 5, I want you to do this on your own on the side in the video, and then come back and we can check your answers for you. Now that you've answered it off to the side, we are going to see how many minutes it increases by. So it increased in the first one by 25 minutes. Then from 55 to 20 is another 25 minutes. So that is what our pattern shows. So to generate the next term, we're going to take the previous time and add 25 minutes. So the next time that we would end up with would be 8:45. Then it would be 9:10, 9:35, 10 o'clock, and 10:25. So hopefully you got that one correct. So on to number 6, the last of our patterns. If we have 3, 1, 4, 1, 5, this one's a little tricky, but if you remember from when you dealt with pi in the past is 3.14, but if you keep on going on, these are actually the digits of pi. To generate the nth term, so that would be any term in the sequence, that you just need to determine the digit of pi that you were working on. So that means that 3.14, 15, 9, 2, 6, 5, and 3 will be the next digits of pi. We are going to use counterexamples when we need to prove that a conjecture is false. So a counterexample is really just an example that shows that the conjecture is false. So it's a very specific example. So try to think of it as what example is going to prove that the statement is not always true in all situations. So for the very first one, we need to determine whether the conjecture is true or false, and then if it is false, we need to provide a counterexample. So for the first one, the sum of any 2 consecutive integers is always odd. So consecutive just means that the numbers come right after each other. So say you have 1 plus 2. If we add those together, we get 3. And we can see that it is odd. So then if we check a few more, so if we think of any other example, so say 4 plus 5, that gives me 9, that those are true as well. So are there any other consecutive integers that makes it so that they're even? And that's never going to be the case. So this is a true statement. So for number 2, the product of 2 numbers is always larger than either number. So we have to think of when we multiply any 2 numbers together, so say 2 times 1, that gives me 2, and that is not larger than the other number. Or we can think of 2 times 1/2. I can even make it smaller and see that half of 2 gives me a 1. We can see that this is not larger than the other number. So in the first one it's equal to, not larger, and this one is definitely smaller than, not larger. So this would be false. And my counterexample would be, could be either of these two, showing that 1 is not bigger than 2. For number 3, the product of 2 perfect squares is always a perfect square. So again, check some examples. So perfect square would be like 4, because the square root of 4 is 2. And say 9, because the square root of 9 is 3. So if I multiply those together, I get 36. And I can take the square root of 36 and end up with 6. So it is a perfect square as well. So that one does work. So you have to think of other possibilities. So say 25 maybe times 1, because those are both perfect squares, comes out at 25 again. And that one also works because we already know 25 is 5 times 5. So there's really no other examples that work or that would prove that it's not true. So this is a true statement. So that will work for any of our perfect squares. When we multiply them, they will still come out as a perfect square. All right, for number 4, the area of a rectangle is 6 meters squared. Then the dimensions must be 2 meters by 3 meters. All right, so off to the side right now, I want you to tell me if this is a true or false statement. And then if it is false, I want you to think of what a counter example could be. All right, so hopefully you put false, that this does not always work. The area will not always be 6, or if the area is 6 meters, the dimensions are not always going to be 2 meters by 3 meters, because it could be 1 by 6, and that would be a counter example I could show so that the area is still 6, but the dimensions are something different. All right, so for number 5, dividing by 2 always produces a number less than the original number. All right, so if you try it, say we have 8 divided by 2 gives me 4, and that is less than the original number. But what about negative numbers? So say we start with a negative 2, or sorry, a negative 8, and I divide by 2. That gives me a negative 4, but negative 4 is actually larger than negative 8. So this would be our counter example for number 5, since that is a false statement. For number 6, vertical angles are never complementary angles. So complementary, remember, means that they add up to be 90 degrees. So can we have 2 vertical angles that are never complementary? Well, we could have it where they are complementary, because what if one of the degrees is 45 degrees and the other one's also 45 degrees? Then 45 plus 45 does equal 90, which means they are complementary. So for number 6, again, we could say that it is false. So for number 7, if A times B equals 0, then they're saying that either A has to equal 0 or B will always have to equal 0. So only one of them has to be equal to 0 at all times. But that works in most situations, but could they also both be equal to 0? And that's where the counterexample is. So this would be false. And our counterexample is that A could equal 0 and B can equal 0, because A times B still will equal 0 if they're both equal to 0 to begin with. So there's our counterexample for number 7. For number 8, we're going to do together again. So if 2 angles are supplementary, or they're saying 2 angles are supplementary to the same angle, must be congruent. So let's think of an example. So if we have an angle over here, say this is 40, and the angle that would be supplementary to it would be 140. So if those 2 angles are supplementary to the same angle, all right, so if my red one right here, and I'm going to do another one similar over on this side, so 140 as well. If those 2 that are circled in red are supplementary to the same angle, so this is 40 in the middle, then these 2 are supplementary and these first 2 are supplementary, then what do you notice about the first and last one? So that these are congruent. So this is a true statement. And for number 9, now I want you to work this one out on your own on the side. So all state names have at least 2 syllables. So I want you to answer, is it true or false? And then also, if it's false, give me an example of a state that does not have 2 syllables in their name. All right, so now that you've answered it, this is false, because there is an example of a state that does not have at least 2 syllables, and that would be Maine. All right, for number 10, for the very last one, squaring a number and adding 1 will always produce an even number. So let's think of an example. If we square, let's say 5, so 5 squared, and we add 1 to that, so that's 25 plus 1 gives us 26. Okay, that one did work. But one thing you want to think of is that when I square 5 squared, I give it an odd number, and then I'm adding 1, so I get an even. So is there a number I can square that will give me an even number to begin with? So when I add 1, it will give me an odd. So let's think of, instead of 5 squared, what about 4 squared? So if we do 4 squared, that's an even number, so it's 16, but when I add 1 to it, I get 17, so that one does not work. So here is my counterexample, which shows that this statement is not always going to be true, so it is a false statement. So one thing I want you to do before you come to class tomorrow is I want you to write your own conjectures, to write 2 separate conjectures, so some kind of statement, and then when you get to class tomorrow, we are going to trade with the people in your group, and I want them to figure out then is your conjecture true or false, and if it's false, they're going to practice writing a counterexample for your statement.